Let's go to the second part of this lecture. We're going to talk about robustness accuracy trade-off. The question that we're going to ask is, if adversarial attack is unavoidable, what can we do? What I want to show you in this part of the lecture is that there exists a natural trade-off between accuracy and robustness. In other words, you can be absolutely robust but useless, or you can be accurate but quite vulnerable. We want to characterize this trade-off, and this again would be a theoretical discussion. Here is what we want to do. We want to look at a paper by Zhang et al., published in 2019, ECE595ML. The paper is theoretically principled trade-off between robustness and accuracy. This paper. You can find the paper on arXiv. So why do we say that you can be absolutely robust but useless? Here is an example where you always claim class 1 regardless of what you see. Now, this classifier is not very useful because no matter what you see, you always say that it is class 1. However, it is extremely robust because no matter how you perturb the input data, it will always give you class 1. You can never fool the classifier. And so this gives you an example where you can get an extremely robust robust classifier. However, it is not that accurate. Now, the opposite is also true. You just download any deep neural network. They are very accurate. However, as we have seen, they are also very vulnerable to adversarial attacks. So we want to characterize this trade-off going a little bit beyond the hand-waving arguments. I want to write down an equation which involves a sum of the robustness and also the natural accuracy. I want to write down the equation, and I want to interpret the results of this equation. There is another paper that I would encourage you to take a look. This is written by this group of authors, which they say that robustness may be at odds with accuracy. This is also available on arXiv. So let me talk about the main message of Zhang et al. In 2019. There are 3 results that were proven in this paper. The first result says that there exists an intrinsic trade-off between robustness and accuracy. And this is something that we're going to look into details today. The second message is that it is possible to upper bound both the robustness term and also the accuracy term using something called the classification calibrated loss. Now, we're going to touch on this topic very, very briefly. And then they also show that you can develop a heuristic algorithm to minimize this sum of robustness and accuracy, this objective function. So we are not going to talk about this topic, which you can easily find a discussion in the paper. What I want to do is to talk about the first 2 components of the paper, and then I will spend most of the time discussing how do we formulate the robustness and accuracy trade-off. Now, in addition to these 3 main messages, the paper also makes 2 very interesting observations. The first thing is that the trade-off optimization is actually a generalization of the adversarial training that we saw before. The other message that they find out is that this method actually outperforms all the NIPS 2018 challenge methods. Now, what is the method that they're proposing? It is the heuristic algorithm that they're proposing to minimize the empirical risk. So what they show is that with their proposed method, they can achieve higher accuracy and maintaining a high level of accuracy. Let us go into the technical details of this paper. In order to discuss the equations, I need to introduce several symbols. In this paper, X is denoted as the input data, and then you can also define the capital X as the random variable with a random realization small x. The labels are either +1 or -1, they're the binary labels. And then the classifier is a mapping from X to Y. Now, they define a thing called the epsilon bar. So the epsilon bar is a set that is centered at X with a radius of epsilon. There is another term that they define, it's called the decision boundary, denoted as dB of f. This decision boundary is a function of the classifier f. So once you give me the f, I will be able to come up with the set of all the x where fx is 0. So effectively what it does is that this is your decision boundary, and here is the equation where fx equals to 0. Then any x that is living on this line is this set. Now, there is one more term, it's called the neighborhood of the decision boundary, or you're putting an epsilon bar surrounding your decision boundary. So what you have is this, you have a band of, or you can call it a margin surrounding your decision boundary, and this is called the epsilon bar B surrounding your decision boundary of your f with a radius of epsilon. Okay, all right. So these are the three definitions given by the paper. Now let us go to the some drawings. Okay, so why is it called the epsilon bar around the decision boundary? Well, you can actually put a data point here, and then you can draw an epsilon bar. Okay. And now you go back to the equation here. The equation says that this B is a set that contains all the x in your set X, such that you can find an x prime inside the epsilon bar of x, such that when you apply your classifier f to x, it has a different sign than applying f to x prime. So you go to this diagram, here is your x, and then you draw an epsilon bar. You ask whether you will be able to find an x prime. For example, here you will be able to find an x prime, and this x prime, when you apply the classifier f, you apply the same classifier f here. Since this is on one side of the decision boundary, this would perhaps it is positive, but your x prime is living on the opposite side, and so it has to be negative. And therefore, when you take the product of x and f of x prime, that has to be negative. This defines this neighborhood of the decision boundary. Then the paper moves on to talk about a terminology called the natural classification error. This natural classification error, again, it is a function on your classification f. Now, inside this f, this classification error, you have an expectation on an indicator function. In this indicator function, you are measuring the event where your classification of an input data point f, when you compare against your label y, these two have a mismatch in terms of the sign. Or in other words, you multiply f with y, it will give you a negative value. And therefore, this means there is a misclassification happens. So when you have this indicator function, you're measuring how many times that you have misclassified the data. And then when you apply the expectation, you're summing over on these examples in your training data set. And therefore, this is called the classification error, and 1 minus this R of nat is called the natural accuracy. And of course, you want this natural accuracy to be as high as possible. There is one more term, it's called the boundary classification error. It's defined as this R of BDY. Now, in this definition, you also have an indicator function. The indicator function is measuring the coexistence of two events. The first event is that your X is living on the boundary of your decision boundary. It's living in the epsilon bond of the decision boundary. The other event is that your classification of X is correct. So you're measuring this event. Now, what does this event means? We can go to the diagram here. Now, suppose you have two regions. One is labeled as +1, the other one is labeled as -1. These are the green and also the pink area. If this is the correct decision boundary, and this is your estimated decision boundary, this is your F, okay? And so now you're going to make an error because you're using a classifier that you come up with, and these are the regions, and these regions, they are the natural error because before I attack you, you have already made these mistakes. Now, what is the boundary classification error? The boundary classification error, as you can see from the equation, it is that first you need to draw the margin, or you need to draw the band that is covering your predicted decision boundary. So first of all, you draw all these red dotted lines. These would define this set of the epsilon bond B surrounding the decision boundary. Now, you're not just looking at all the values inside this band, you're also looking at the intersection with the other event where it is correctly classified. Now, what is correctly classified? The correctly classified regions would be regions where it is living in the band and it belongs to the class which is correct. And in this case, it will be this area and it will be this area. Now, the sum of the natural error and also the boundary error will define what we call the robust classification error. So here, the robust classification error is defined as the sum of these two terms. So the first term says that this is the natural error. This is even before I attack you, you are going to make a mistake. The other part says that if I indeed attack you, what will be the mistake that you're going to make? And so these will be capturing the boundary error, and this is capturing the natural error, and then the sum will define what we call the robust classification error. And this is the thing that we want to minimize. Now, at this point, you may feel that, okay, I have this natural accuracy term here, and this is somehow measuring the robustness. But how should we actually solve this optimization problem? And this is more like a high-level argument that it has not gone to the level of allowing us to develop any algorithm. So in the following slides, what I want to show is that you can start with this point and try to characterize what we call the robustness and accuracy trade-off. Before I go to the technical discussions, let me try to give you an example in order to convince you that robustness and accuracy, they cannot come all together. Here is an example distribution. Let's say your input X is living in the space of 0 and 1, and then the true label is either +1 or -1. And so here is the range of X which you can live. And then you are going to partition this X into many segments. Each segment has a length of epsilon, and this epsilon, of course, is defined by you. You pick the epsilon, and then I am going to define this partition. The partition says that as long as you're in the odd segments, like let's say here, 1, 3, 5, 7, you are going to give a the label would be -1. Otherwise, the label would be +1. So this is the distribution of the input data. And then you can also define the posterior probability. The posterior probability says that if you give me this x, the probability of getting y equals to +1, it will be 1. Otherwise, it will be 0. And you can do some simple calculation to show that this is indeed a good posterior probability. Okay, so now I give you this posterior probability. Then I can calculate what is the natural error, what is the boundary error, and what is the robustness error. Now, we call that this is the posterior probability. And so if I ask you, if I want to construct a Bayesian optimum classifier, what would you do? Well, what you would do is that you're going to say that my class has to be the class that can maximize this posterior probability, the map decision rule. And so if you go with this Bayesian optimum, then the Bayesian optimum would say that your decision rule has to be the one that maximizes this posterior probability. In this case, the posterior probability is magically matching with the underlying true distribution, and therefore, when you choose this posterior decision rule, you are going to make an absolutely correct decision. Because why? I give you an x, and then you will say that I want to return you a 1 when this posterior is maximized. Now you can only have two choices. You can only plug in y equals to +1 or y equals to -1. If you plug in y equals to -1 and you are here, then certainly the posterior will tell you it is 0, and so you will choose so if you're here, if you choose if you're choosing y equals to -1, then the posterior is 0, and certainly you will say that I would choose the decision to be +1. Okay, so the posterior probability, if you try to maximize the posterior probability, then indeed you are solving the Bayesian optimum solution. And therefore, the Bayesian optimum classifier will have an error of 0. Now, what is the boundary error? The boundary error is big, because the boundary error says that if I'm here, I can just draw an epsilon ball surrounding myself. Then you can see that within the epsilon ball, you can always find a sample that is misclassified, and therefore the error is 1. Now, when you sum these two up, you will see that the robustness error is actually the sum of the two, it is 1. Now, the other example is to choose a all-1 classifier. What do I mean? Well, I don't really care about this posterior probability anymore. I'm always giving you 1. And now, if you give me 1 always, then I can calculate the natural error, which is the Bayesian error of this case. If it is indeed 1 and I claim 0, I claim -1, then I will have the probability of making an error. And since it is the partitioning the space into 2 halves, then the probability of getting this natural classification error is 1/2. How about the boundary error? The boundary error is actually 0 because you're always claiming 1. Okay, and so there is no way for you to make a mistake in terms of this perturbation, and therefore your boundary error is always 0. And if you sum the two, this is actually optimum in terms of the robustness. Therefore, this example shows you that if you are trying to minimize with respect to just the natural error, you are going to come up with this Bayesian optimum classifier, which is not very robust. On the other hand, if you choose a very, very stupid classifier or 1 classifier, you can actually minimize the robustness. Okay, after discussing this example, I think we are ready to go into the technical details of this theory. So what these authors they have shown is that they want to compare this robustness error compared to this natural error with a star. Now, what is this star? This star is the minimum of all the possible natural error evaluated at different f's. And so you want to bound what? Well, you want to find an upper bound on this quantity. And so you will know how far is your robustness error compared to the natural error by what amount. In other words, if you go to the equation here, this one gives you an upper bound on this quantity. It says that the robustness error, certainly it will be bigger than the natural error, because the natural error is the error that you don't care about the robustness. You just want to minimize your natural error. And so this is this robustness. If you find a good F, of course it was going to be bigger than this R star. And so you're going to find an upper bound on this quantity, and this upper bound will say that your robustness error is less than or equals to your R star plus whatever that is remaining there. So if you can find this upper bound, if you can prove this result, now we haven't really talked about this quantity yet, but suppose we can really prove this result, then we can, if we can also link this upper bound with some interpretable notions. For example, can we say this is really measuring the robustness, or this is really measuring the natural accuracy? Then perhaps by minimizing this upper bound, I will be able to do a control over the quantity on the left-hand side. So what can we do now? Well, what we want to do is to evaluate this upper bound here. We are not going to talk about the proof of how to get to this upper bound. We are going to just tell you briefly what would be the steps to get to this upper bound. And then we are going to interpret this upper bound to give you some idea of where does this robustness and accuracy come from. The argument of this proof is fairly long. So what I want to do now is to give you an overview of how they argue for this upper bound. Now there are 4 steps, A, B, C, and D, which we will go into the details one by one. Now let's just look at step A. Step A should be pretty straightforward. It says that the robustness error minus the R star is just equal to the natural error plus the boundary error minus R star. Now this really comes from the definition of the robustness error. And so this should be okay. Now what we want to do next is to talk about steps B, C, and D. And then we're going to look at just this equation and make some interpretations. Let's first look at step number B. The step B says that you have this robustness error minus R star equals to the sum of the natural error and the boundary error minus R star. And then the B step says that I am going to upper bound this quantity by something like this. Now certainly the boundary error is the same, so we can skip the discussion. We just need to look at the difference between R natural and R star natural. And it turns out that this difference can be upper bounded by a function's inverse times another pair of functions. So what are these functions? These functions, they are called the classification calibrated surrogate laws. So I need to really tell you the meaning of this psi and this phi. Okay. Now, the motivation of using this pair of equations is that if you look at the definition of the natural accuracy and natural error, it is really defined using this indicator function. Now, the indicator function is a 0-1 loss function, and it poses a lot of difficulty because it is not differentiable. And so over the past couple of years, researchers have proposed surrogate functions to replace this 0-1 loss so that we can do some analytics. And so the surrogate loss of this 0, 1 loss function is given by a pair of functions phi and psi. Now, the phi function is given by here, and then the psi function is given by here. And you can see that if I choose the hinge loss, then the psi function will just be the identity operator. So why is this true? Well, it is because that if you draw the 0, 1 loss, the 0, 1 loss has a shape like this, and then the hinge loss has a function like this. And so you can always upper bound the 0, 1 loss using this hinge loss. Now, the derivation of the psi function requires some kind of convexity arguments, which we are going to skip the discussion here, because that would also involve something called a conjugate function, which is way beyond the context of this course. Okay, but the bottom line message here is that if you want to bound this natural error, you can look at this indicator function, and then the technique here is to introduce the concept of surrogate loss by using a pair of functions phi and psi, and then you can write down the equation in this form. Okay, so here are some additional discussions about this phi and psi function. And so if you choose to use the hinge loss, for example, this one, then this phi function will be given by this equation, and psi will be the identity operator. Now, substituting these equations into the equation before, then you can show that the robustness error minus the R star will be upper bounded by this quantity. Okay, so instead of dealing with the 0, 1 loss, you can actually handle the a differentiable surrogate loss. And now, once you have the surrogate loss, in terms of computation, it will be a lot easier. And this is how you can develop an algorithm to solve the problem. Now, how do we bound this error? This error turns out that it can be upper and lower bounded by this quantity, which I'm not going into the details. Okay, so if you read their theorem 3.2, you will be able to see that they are able to upper bound and lower bound this quantity. This is using the surrogate functions. Now let's move on and talk about steps C and D of their derivation, and then we're going into the last step to talk about the interpretation of their main theorem. So what is step C? Step C is just the definition of the boundary error, so we can skip that. Now D follows from the following argument. D says that you start with this probability of the epsilon ball surrounding a decision boundary, which is the band, and also you have this intersection. So this is really defining the boundary error. And now this probability can be upper bounded by just the first event, ignoring the second event. Well, because why? Well, because you're taking the intersection between the two events, and certainly this is a bigger event than the intersection of two events, and therefore the probability of the former will be less than the probability of the latter. This probability, if you apply the indicator function, you can show that this probability is equal to taking the expectation over all the x primes subject to this maximum in this epsilon ball. And when you take the indicator function, you'll be able to show that this expectation is the same as this probability. Now, if you're not following, you can just write down this indicator function. It will give you a Bernoulli random variable. And so when you calculate the Bernoulli random variable, there will be case of 0, case of 1. They have probability of getting 1, probability of getting 0. That will give you to this probability. Now, this equality says that since I'm just looking at the event that fx prime is not the same as fx, then this is the same as just that you're taking the product of the two, it will be less than 0. And this also holds if you divide everything by a certain lambda. And for any lambda, this will hold. The last step is to replace the indicator function by your surrogate function. Now, this is true, as I drew you before, is that your surrogate function, for example, your hinge loss function, it is higher than your indicator function, your 0,1 loss function, and therefore this inequality will hold. So after you have gone through all these derivations, you will end up with the equation as follows. You will find the upper bound for the robustness error minus the natural error, and you can show that this is less than or equals to this quantity. Okay. Now, if I'm trying to solve an optimization problem and I realize that this problem is very difficult to solve, then I can perhaps just solve the upper bound problem by minimizing this quantity. How do we interpret this quantity? This quantity you can interpret as two ways. The first term is telling you the accuracy. Now, why do I call it the accuracy? Now, ignoring the psi inverse, because if you choose a hinge loss function, this is identity operator. Now, this is just a surrogate loss, okay? It's a replacement for your 0,1 loss. This is the natural error for your F, okay? So you want your classifier F to have a natural error that is not deviated too much from your optimum Bayesian classifiers. Okay, so this is really defining the accuracy. The best you can achieve, if you ignore anything here, then the best that you can achieve is to find an F that can make this 0. And if you ignore that second term, then you will indeed be able to find the Bayesian optimum classifier, which will give you this error to go to 0. And so this is a good term of measuring the accuracy of your current classifier F. Now, if you ignore this term by just looking at the equation here, this is what? Well, if you remember, this is actually an upper bound of this probability of boundary events. Okay, and so this is really measuring the robustness of your classifier. Now, if you just try to interpret the result in this way, you can also interpret fairly easily. Here you have a sample point x prime and x. You want them to be misclassified. And then you have an indicator function, or here you have a surrogate function. And then you're finding the worst case among everyone. And therefore, this is really measuring how many samples are living inside the margin. And therefore, this term is defining the robustness of your classifier. And so if you try to minimize the sum of these two, then effectively, you are minimizing the trade-off between the accuracy and also the robustness. How do you tune up the emphasis on accuracy versus robustness? Remember that you have a parameter lambda, which you can tune. And so if you rearrange the terms, for example, pulling the expectation outside, then you can end up having this equation where you have minimization over the expectation of the accuracy plus the robustness. Now, this accuracy, you can see that in this equation, I'm further replacing this term by the natural accuracy, which is the product of your F times your Y. If they match, and if you set it to a surrogate loss function, that will give you a small value. Otherwise, it will give you a big value. So this is really measuring the accuracy. Now, in this equation, you can see that the lambda is here. And so for any trade-off, I need to pick a lambda in order to get you to the right operating point. Now, this is the key message of the paper, which says that for any classification problem, if you want to handle robustness, in other words, if you want to handle adversarial attack, then this would be a good optimization problem to solve. Certainly, you need to find this parameter lambda, but given that the lambda is determined, then this will really be the optimum formulation in a sense that you're not just maximizing the robustness, at the same time, you're also trying to ensure that your accuracy error, your error in the natural sense is minimized. So what do you gain? Well, you gain this trade-off between accuracy and robustness, which has not been shown in the literature before. And this is a major contribution of this paper by Zhang et al. Now, you can also compare this minimization with the typical adversarial training by, for example, by Marjorie et al. So what the adversarial training does is to minimize the expectation of the maximum loss of this function. And here I'm replacing the 0, 1 loss by any surrogate loss. And you can see that there is a very, very similar formulation between these two. However, there is also some subtlety between these two optimizations. First of all, this problem, adversarial training, does not have any accuracy term. And secondly, here you are just replacing the y's. You're using the actual label y's, but here you're using the boundary where you have a sample x, which is correctly classified. And so here is the two difference. One is that you have an accuracy term. The other one, you have a modified robustness term. Adversarial training is mainly focusing on just the robustness term. And so you can also view this as overall, this function will be an upper bound on this entire term, ignoring the effect of this accuracy. Okay, so up to this point, we have been able to see that there is a natural trade-off between the accuracy and also the robustness. The take-home message of this part of the lecture is that whenever you try to minimize the adversarial error, in other words, whenever you try to do some kind of adversarial training, do not forget that you also have the accuracy that you want to maximize. If you only try to maximize robustness but forget about the accuracy, you will be able to get a classifier which is not very, very accurate. So to summarize, there are two messages of this entire lecture. The first message is that all classifiers are vulnerable. So if you're still thinking about attacking and defending classifiers, just bear in mind that there is a fundamental phenomenon that's driving this study, which says that all classifiers are indeed vulnerable. And then the second message is that there is a natural trade-off between the accuracy and also the robustness. Now, I want to give some general advice to students who want to work in this area. As I said in the last lecture, I think it is not a good idea to work on a problem which is trying to develop new attacks and new defense. One, this area is highly saturated. And two, it is just not a very interesting problem because given the obfuscated gradient approach, many defense mechanisms can be defeated. Now, certainly you can develop methods that can overcome this issue, but as I have shown you in one of the slides, this is an endless game where today you have a better defense, but tomorrow you have a stronger attack. And so this is also not solving a problem that has a significant value in the sense that I showed you last time. There are many problems that we encounter the physical space. So if you try to launch an attack in the physical space, you will not be able to succeed in attacking. Similarly, even if you try to attack in the cyberspace, there are other considerations which is unlikely to be adversarial attacks as the way that we're describing. The trade-off analysis here, it is very useful. However, on the other hand, you can also say that this is kind of expectable because if you want to have higher accuracy, it is certainly that you need to trade your robustness. The more difficult question, in my opinion, is to go beyond the LP ball because right now, all the studies that you have seen in the literature, they are based on LP balls. And so these attacks, they are all very localized to a small LP ball space. And you can see that in any adversarial attack in the real physical space, for example, you can have a shadow, you can have an illumination change. These are already beyond what an LP ball can describe. So these are the more difficult problems that you may want to consider. what would be more valuable to study, in my opinion, it would be to improve the natural accuracy, just the natural accuracy and not the robustness in different environments. And don't worry about the customized attack, because when you really want to develop an autonomous car, you're going to test it on different environments. And these environments require you to have a really robust classifier. And no one is going to hack into your system, at least at this stage of the development. And so what you should really spend your energy on is to develop a method that is very, very good in terms of the natural accuracy, and do not fail easily when you go from one situation to another situation. If you really want to study adversarial attack, then my advice is to develop methods that can defend attacks at scale. Now, what do I mean by at scale? It has to be able to defend attacks with very, very large volume, with a lot of variety of attacks, and with different forms of attacks. You cannot assume that you have seen examples before. You have to be able to generalize to attacks that you have not seen. And so the adversarial attack problem, it is a very intriguing problem. It's a very interesting problem that brings to the entire community the problem of robust machine learning. I think robust machine learning, it is a very, very hot and very, very important area. I encourage you to consider working on this important problem. For adversarial attack itself, I think it has limited scope. But if you're interested in, as I said, you should consider problems that are beyond what people have been doing so far. So this is the end of our discussion on adversarial attack. If you go to the project page, you'll be able to see our project on adversarial attack. I encourage you to spend time and start early on this project. And if you go to the last part of this project, you will be able to see questions asking you to read some recent papers on attacking and defending a classifier. And I wanted you to really try to read some of these recent papers and build up your reading skills, and also try to write a technical report to the best you can. So we will have one more lecture on conclusion. In the conclusion lecture next time, we are going to summarize what we have learned so far throughout the semester. So I will see you next time.